Textbook section 8.3 and question number is 13. So for this exercise, we have to estimate the minimum sample size needed to achieve the given margin of error. And somebody just told us that margin of error, which is denoted by E or ME, whichever notation you want to use, that's fine, is going to be 4 percentage points or 0.04. What sample size should you pick to guarantee a margin of error of this? So we know that for a 95% confidence interval, margin of error is simply 2 times the standard deviation of the sample proportion if we're dealing with proportion, and sample mean if we're dealing with sample mean. And we have also seen previously that in the case of proportions, the sigma turns out to be square root of p into 1 minus p divided by square root of the n. So now let us solve this equation, i.e. modify this equation a little bit so that we can solve for this n here. Now if I multiply both sides by square root of n, I get margin of error times square root of n is equal to 2 times square root of p into 1 minus p. And then if I divide both sides by margin of error, I get square root of n is equal to 2 times square root of p into 1 minus p divided by margin of error. And that simply means if I take squares on both sides, then square root of n turns out to be 2 times square root of p into 1 minus p, this thing whole squared, divided by margin of error whole squared, i.e. n turns out to be 2 times square root of p into 1 minus p whole square. So if I take square of this 2 square is 4, and then if I take whole square of this square root of p into 1 minus p, I can just get rid of this square p in that sense. So this is going to be p into 1 minus p over margin of error squared. Now we have to modify this a little bit because the question did not give us any value of p or p hat for that matter. We however know that the product of p times 1 minus p can never be bigger than 0.25. Let me show you some example proportions. In this file, I took some imaginary, arbitrarily chosen p hats and 1 minus p hat. If p hat is 0.5, 1 minus p hat is 1 minus 0.5, which is 0.5. If p hat is 0.6, 1 minus p hat is 0.4, so on and so forth. And on the third column, I took the product of this p hat and 1 minus p hat, and looks like the maximum possible value of the product is 0.25. All the other values from other possibilities of p hats and 1 minus p hats is less than 0.25. So now we can just approximate our margin of error by saying, hey, you know what, when we don't know the true p or p hats, then at least we know that the product of these two animals is maximum 0.25, and therefore if I replace this guy with 0.25, I know the maximum possible value of the fraction on my right hand side, i.e. I have the maximum possible value of the number of observation. So notice that 4 times 0.25, sorry, that was my mistake, it should have been 0.25 here. Notice that 4 times 0.25 gives us a value of 1. Sorry, I made another mistake here. This on the denominator is margin of error squared. So 1 over margin of error squared gives me an approximate value of n, which I can use to achieve my desired level of margin of error. So if you don't want to worry about all this logic and intuition, just use your cheat sheet. Write this thing down on your cheat sheet during your exam or quiz, and if I ask you to find a sample size needed to achieve certain value of margin of error, you just plug in the value of margin of error in this equation. So let's do that for this question. My margin of error, which I desire, is 0.04, and therefore n is going to be 1 over 0.04 whole square. So let's use the calculator to find the value of 0.04. 0.04 times another 0.04 would give me the square value, times 0.04 is equal to 0.0016. 1 over 0.0016. And if I take 1 divided by 0.0016, I get a number 625, and that would be the number of observations to guarantee a margin of error approximately 0.04. I hope that helps you understand how to attack a question like this. If somebody asks you to find the optimal value of n given a margin of error, use this formula and you will get your result in 1 minute. I'll try to be back with some more answers later on. For now, bye bye.